All righty, welcome back, everybody. We're going to continue on with Chapter 5 in the ideal gas law. So, of course, the ideal gas law is an equation you've seen before. It's PV equals nRT, where it's pressure times volume, N is your number of moles, R is the ideal gas constant, which you see here, uh, and then T is temperature in Kelvin. Uh, okay, so by the time we're done with this chapter, you'll have two ideal gas constants. Do you know how to use them? Pay attention to the units. So you see this one here has liters, atmospheres, kelvins, and moles. These will be for your gas calculations. The other gas constant we'll use throughout the rest of the Chem 1 and Chem 2 is will have units of joules in it. So that'll be for energy calculations. So just kind of pay attention to the units so you know which one to use. And so, how do we get to the ideal gas law? Well, we have our three laws we talked about. Boyle's law, remember that was P equals a constant, which means that so if we move this around, we're going to get everything in terms of volume. That's going to be K over P, or K times 1 over P, which is, you remember, K is a constant, and so we can go backwards. If we just take that constant out, that means V going to be proportional to 1 over P. As we talked about yesterday, that means that V is inversely proportional to P. Okay. Charles's law. That is your V over T equals your constant. We're going to move everything around to get V by itself because we're going to compare these through volume. And so, of course, you remember now B is your proportionality constant. So if we take it out again, V is directly proportional to T. And then we had Avogadro's law. And that one was volume over number of moles equals a constant A. So if we get volume by itself, that's going to be A times your number of moles, or volume is directly proportional to your number of moles. Now, if we take these proportionalities and we put them all together, so let's see, what is V going to equal? V, well, still dealing with proportionality. Okay, so V is proportional to 1 over P, T, and N, which means that V is proportional to temperature times number of moles over pressure. And now, of course, to get a new equality, we need a proportionality constant, which we know as the ideal gas constant. So that means V equals R, temperature, number of moles over pressure. And we can rearrange this into V equals nRT over P. And then we end up with PV equals nRT. This is a short derivation. Here in a little bit, we'll look at the kinetic theory of gases, and we'll do a longer derivation. So we can actually get to the ideal gas law from first principles. Okay, so let's actually work a problem with the work through an exercise with the ideal gas law. I was going to go ahead and do the kinetic theory of gases now, but I didn't notice that the textbook had it already lined out in the chapter, and I'd like to stay consistent with the sections of the chapters. So, person accidentally swallows a drop of liquid oxygen, so O2, which has a density of 1.149 grams per milliliter. Assuming the drop has a volume of 0.050 milliliters, what volume of gas will be produced in the person's stomach at body temperature, which is 37 Celsius, and a pressure of 1 atmosphere? Now, as you can see, I think this exercise focuses on the wrong question. I think the problem is how do they get a drop of liquid O2 in the first place, and how they swallow it? Uh, Liquid O2 is, well, it's part of rocket fuel. It's cryogenic. You're not just going to swallow it by accident. That'd be incredibly painful. So I just sometimes you look at questions in textbooks and go, not a realistic scenario, but okay. But let's see, what's it asking us for? The volume. What do we have? Density, 1.149 grams per milliliter. Let's see, oxygen, of course. We have the molar mass of oxygen. Pressure is 1 atmosphere. Temperature, 37 Celsius. And I'm going to go ahead and write down R, 0.08206 liters, atmospheres over moles times Kelvin. Now, look at the units of the ideal gas constant. I strongly suggest you just take every other quantity that you're going to be working with and make it match the units. So you see, we already have atmospheres, but we have degrees Celsius and not Kelvin. So we're going to need to change that. Okay, so all right, so we're just going to start in with our ideal gas law. Oopsie. And we're going to solve for volume. Okay, now we have RT and pressure. However, we don't have a number for moles. Okay, so we do, and so let's adjust this just a little bit up here. So this is O2 gas. We have a volume of O2 liquid from the problem. And so what can we do to get number of moles from that? Well, I know that my molar mass of O2, and let's move this. It's going to be 2 times 16 equals 32 grams per mole. So that's in grams per mole. So what I'm going to need is so just like we have been doing our grids, I'm going to need to take a mass of liquid O2 and divide by that molar mass. Okay, well, how do I get a mass? Well, I have a concentration of the liquid. I have a density. So this means that your number of moles is going to be your 0.050 milliliters times your density over molar mass of O2. We can shorten this down, 0.050 times the density. Okay, so now we can plug that in. Our volume is now going to be 0.050 times rho over times R times T over P. And again, if this calculation for number of moles is confusing, go back to what we were doing before. Like, let's say we had 3 grams of O2, and we know that it's 32 grams per mole. That's what we're doing. We're taking our mass and dividing by our molar mass. Okay, so now this is essentially going to be its own fraction, 0.050 rho. And that's just going to give us 0.050 rho RT over the pressure times the molar mass of oxygen. Okay, we can actually, with all the numbers we have, we can actually plug numbers in here. One last thing we have to change is we have to make sure that temperature is in Kelvin. So this will be 310 Kelvin. Okay, so then volume is going to be 0.00. Density is 1.149. Our gas constant, well, let's see here. We can also chase our units. It was milliliters, I believe. Yep. So then we have 1.149 grams per milliliter. Zero 0.08206 liters, atmospheres over moles, Kelvin. And then temperature is 310 Kelvin over pressure, which is 1 atmosphere. And then the molar mass of oxygen is 32 grams per mole. Now, when you work all of this out, you're going to get 0.0457 liters. And you may ask, well, how do I get that when I have milliliters in the problem? That's because milliliters divided by milliliters, that'll cancel out. And at the end, you'll have liters left. So then we want significant figures. So you can either have your answer as 0.046 liters or 46 milliliters. If it's not specified, I don't care if you just leave it in the unit you solve to, that's fine. But some people might want to turn it to milliliters, that's also fine. It doesn't matter. Okay, another one. Bicycle tires filled with air to a pressure of 75 psi. Remember, that's pounds per square inch. At a temperature of 19 Celsius, riding the bike on asphalt on a hot day increases the temperature of the tire to 58 Celsius. The volume of the tire increases by 4%. What is the new pressure in the bicycle tire? Now we are going to work with the ideal gas law, and we're going to try and figure out what's constant versus what changes. So what we're being asked for is essentially a new pressure, where we have our first pressure is 75 psi temperature 1 is 19 Celsius, temperature 2, 58 Celsius, and volume 2, oopsie, is 4% more than volume 1. Okay, so if we start with our ideal gas law, we say, well, what changes and what's constant? Okay, so we see pressure changes. We see that temperature is going to change. The volume is definitely going to change. So that means that your number of moles and R are going to be constant. And so what we're going to do is we're going to rearrange the equation to get variables on one side, constants on another. So that means if I divide through by T and I get PV over T in R, my left side of the equation is variables. My right side of the equation is a constant. Now, as we have seen with our other laws, anytime we have uh, um, an equation involving values that are equal to a constant, every instance of that combination of values is equal to the same constant. So we now know that in situation 1, P1 V1 over T1 is going to equal P2 V2 over T2 because they both equal the n times R constant. And so then I can solve for P2. That's going to be P1 V1 T2 over T1 V2. And now I just need numbers to plug in here. Now you notice that we don't have to worry about the ideal gas constant. I still want you turning temperatures into Kelvin because it's a good practice to be in. Because otherwise you will run across problems that you get wrong because you didn't switch to Kelvin. So temperature 1 is 19 Celsius. And that's going to be 292 Kelvin. Temperature 2, 58 Celsius. Oopsie. 273. That's going to be 331 Kelvin. All right. Now we have to deal with that 4% increase. So what does that mean? So 100%, remember, is 1. An increase of 4% is 0.04, which means a 4% increase is going to be 1.04. Okay. So that means that V2 will equal 1.04 V1. Go back and review some of your percentage mathematics. Make sure you're wrapping your mind around this. Okay, so that works out because you notice we weren't exactly given volumes. So how do you plug those in? Well, if I plug this 1.04 V1 in for V2, V1s will cancel out. And so we won't have to worry about volume. So let's look at that. P2, P1, V1, T2 over C1. And now I'm going to plug in 1.04 V1. So it's going to be P1, V1, T2 over 1.04 V1, T1, and you notice V1s will divide out. So our equation changes to P1, T2 over 1.04 T1. And so now we can plug in our numbers. Now, once you're getting this far, before you start plugging in numbers. Again, we're trying to build skills. Some of you may have them, some may not, but we're just going to work on them. Here, this is going to be P1 is 75 psi. T2 is your 331 Kelvin over 1.04, and then T1 is 292 Kelvin. This is going to give us 81.7 psi, or adjusted for significant figures, 82 psi. So again, sometimes you're going to have to think of the ideal gas law in terms of what's variable, what's constant. Separate them apart, and then know that every instance of those variables is they're all going to equal the same constant, like we were doing with the other laws. All right, so gas stoichiometry. So now we come across the idea of molar volume. We can actually change the ideal gas equation around. So molar volume is going to be, okay, let's say liters. So liters per mole. That's why we have V over N. And that'll leave us with RT over P. And so molar volume, as it says here, is an intensive property. It means it remains constant regardless of total sample size of a specific gas. You can compare that to an extensive property, so total volume. For example, total volume will change if you just add more gas molecules. But molar volume is dependent on the number of moles of gas you put in. So molar volume is going to pretty much it's going to be in that intensive property. It's going to be for like O2. For every mole of O2 you put in, you're going to get a certain volume. And that's what it means by intensive. We also talk about doing problems and whatnot. So here's two things I would really lock in on these because you'll see these on standardized exams. You need to know the difference. Standard temperature and pressure, or STP, is different than standard conditions. Now notice the pressure is the same for both of them, but the real difference comes in at temperature. Standard temperature and pressure is 0 Celsius in 1 atmosphere, versus standard conditions would be what you experience. It's just standing in your room or in a lab somewhere. That's the temperature 25 Celsius and 1 atmosphere. So if we want to get a better idea of molar volume, if we look at an ideal gas, so gases that are going to obey the ideal gas law, your molar volume is going to end up being about 22.42 liters for every mole of a ideal gas that you put into a system. And so, and again, that's intensive. So let's look at our next exercise. Sulfur trioxide is produced by the production of during the production of sulfuric acid by this system of equations. What volume of O2 at 350 Celsius and a pressure of 5.25 atmospheres is needed to completely convert 5 grams of sulfur to sulfur trioxide? So you have to think of this in two parts. We're going to need a total, so we're going to need moles of O2 from equation 1, moles of O2 from equation 2, and we're going to need to add those together. Once we get that, we can use the ideal gas law to then figure out the volume of O2 once we have total moles. Okay, so I'm going to kind of do this in a step-by-step process. Some of you will go, why do I need to do all those steps? That's logic. It is, but we just want to make sure you're getting the logic. I'm not just going to assume that you know the logic. You have to prove to me you know the logic, and then we can maybe not do so many steps. Okay, so for the first equation, the SO2 from here is going to feed into the second equation, so we have to know how much we get, okay? So, okay, so what are we being asked for? Volume of O2 at the end. Okay, what are some things we know? Our pressure, 5.25 atmospheres. Let's see. Our gas constant, 0.08206 liters, atmospheres over moles, Kelvin. Let's see. The mass of our sample, the mass of sulfur, that is 5 grams. Temperature is 350 Celsius. So let's also get, so from the periodic no, that's pressure. I don't need phosphorus. Sulfur is going to be 32.07 grams per mole, and oxygen is 16 grams per mole. So here's a good list that'll help me solve the problem. Okay, so we're going to start with how much SO2 do we get in sulfur plus O2 yields sulfur dioxide. Okay, so just like we've been doing, 5 grams of sulfur 32.07 grams per mole sulfur. And then I get 1 mole of sulfur to 1 mole sulfur dioxide. We get that from the chemical equation. This is going to give us 0.156 moles of SO2. Now, we also know that we're going to be using oxygen in this first reaction. So how much oxygen did we use? Okay, so if I have 0.15 moles of SO2, then I look and I say, well, according to the chemical equation, 1 mole of SO2 reacts with 1 mole of O2, well, produced from 1 mole of O2, we're going to get 0.156 moles of O2 used. Now, this is what I'm saying, like, this is, it looks like extra steps we don't need, but I want to make sure that you're showing me that you're using these chemical equations, the mole to mole ratios properly, that you're properly doing stoichiometric calculations. Once I'm certain of that, we can move on. But because you look at this and go, well, everything has a coefficient of 1 in that equation. So yeah, I mean, SO2 and O2 is a 1-to-1 ratio, so of course it's 0.156 moles of O2. Great. I'm happy you realize that. Prove it to me. Okay. Now, we're going to have to hold on to the moles of O2 used. We're going to take this moles of SO2 produced, and we're going to say how much O2 is used in our 2 SO2 plus O2 is going to give 2 sulfur trioxide. Okay. Well, So 0.156 moles sulfur dioxide is now going to be used. And so 2 moles SO2 is going to react with 1 mole of O2, and this is going to give us 0.078 moles of O2 used in the second step. Okay, so now we say total moles of O2 used. Well, and the reason we went for moles, I hope it's obvious, because in our ideal gas equation, so N is going to be the moles of O2 used, and that's 0.156 plus 0.078 equals 0.234 moles of O2. So that's our variable N for our ideal gas equation. Okay, now we can solve for the volume. Now let's see. PV equals nRT. Volume is what we're solving for. nRT over P. Let's see, R has kelvins, so let's just go ahead. So temperature is 350 degrees C plus 273. That's going to be 623 Kelvin. Okay, so now I'll plug in numbers. V, our number of moles, 0.234. Our ideal gas constant, 0.08206 liters times atmospheres over moles times Kelvin. Temperature, 623 Kelvin. And then our pressure, remember, is 5.25 atmospheres. Everything matches the units in the ideal gas constant, so we'll be good. Our volume is going to calculate to be 2.28 liters of O2 is needed or used in the entire process. All right, let's take a look at another exercise. Let's see. Urea is used as a nitrogen source in fertilizers. It's produced commercially by reacting ammonia with carbon dioxide. Let's see. Ammonia at 223 Celsius and 90 atmospheres flows into a reactor at the rate of 500 liters per minute. Carbon dioxide, 223 Celsius and 45 atmospheres, flows into the same reactor at 600 liters per minute. What mass of urea is produced per minute by the reaction, assuming 100% yield? I hope you will notice quickly what kind of problem this is. I'll tell you in a minute, so kind of work on that. So, what we're being asked for, mass of urea. Okay, well, temperature is 223. I don't need a temperature for each gas because it's the same. Let's see. Volume of ammonia is 500 liters because you notice how it says how much is produced per minute. So we're looking at this reaction 1 minute at a time. So at the end of the first minute, 500 liters of ammonia has been pumped into the system. At the end of the first minute, the volume of CO2 is going to be 600 liters. Okay, so this happens every minute. Let's see, the pressure of ammonia is 90 atmospheres. The pressure, carbon dioxide, is 45 atmospheres. Let's see. Okay, so and then hydrogen, because you notice you know this is going to be a stoichiometric calculation, so moles are going to be involved. But then it says, what is the mass of urea? So I hope your mind picked up on, oh, I'm going to need a molar mass. So let's get all these numbers down. Nine carbon. And as you're doing, I mean, as you're doing assignments, your lists don't have to match mine. I just want to see you making a list of quantities you think you might need that'll help you. As you get better at it, you notice that your list will contain exactly what you need. So now, what kind of problem is this? Do you see how I have an amount of one reactant and an amount of the other reactant? Well, when I have exact amounts of each reactant, that means this is going to be a limiting reactant problem. So I have to know which one of these is limiting. All right. To do my stoichiometric calculations and find my mass of urea, I'm going to need moles of each reactant. Moles of ammonia. We'll start out by saying, well, I know I'm going to be using my ideal gas constant, 223 Celsius plus 273. That is going to be 496 Kelvin. All right, so, okay. We're going to solve for number of moles in is going to be divided by R. All right, so moles of ammonia, let's see, 0.08206 liters, atmospheres over moles, kelvins. T is 496 Kelvin. Okay, so pressure for ammonia, 90 atmospheres. And then volume is 500 liters that was pumped in. It's pumped in every minute. So every minute, the moles of ammonia that we get is going to be 1.1 times 10 to the third moles of ammonia. All right. Now, moles carbon dioxide. So again, we're using our N equals PV over RT. All right, so 0.08206 liters, atmospheres over moles times Kelvin. Temperature is 496 Kelvin. For the CO2, pressure is 45 atmospheres. And then volume is 600 liters every minute. This is going to give us 6.6 times 10 to the second moles of CO2 every minute. Now, we're going to need to figure out using our chemical equation moles and then ultimately mass of urea produced. Okay, so, well, H2, NCO, and H2. That is going to be four H's, two nitrogens, plus a carbon, plus an oxygen. Four. And let's go down here. 4, 1.01 plus 2 of nitrogen is 14.01 plus carbon 12.01 plus oxygen 16. This is going to give us a molar mass of 60.06 grams per mole. Okay, now we're going to check each reactant. NH3, urea. All right, so my moles of NH3, 1.1 times 10 to the third. Now, you don't have to do this. I did because I'm trying to calculate grams per minute. So since I know the whole thing ends up per minute, I'm just going to put minutes in the denominator. Okay, now I go back up to my equation here. And you see it's 2 moles of NH3 for every 1 mole of ammonia, or not ammonia. 2 moles of ammonia for every 1 mole of urea. Okay, so that's 2 moles NH3, 1 mole of urea. And then urea is 60.06 grams per mole. And when we calculate this all up, we're going to get 3.3 times 10 to the fourth grams of urea per minute. Okay, well, what about carbon dioxide urea production? Okay, so our moles of carbon dioxide that we calculated every minute is 6.6 times 10 to the second moles CO2 per minute. From our chemical equation, that's 1 mole urea to one produce from 1 mole carbon dioxide. And then our urea is 60.06 grams per mole. This is going to give us 4.0 times 10 to the fourth grams of urea per minute. Now we look, you notice that the ammonia produces less urea per minute. So our answer to this problem is the 3.3 times 10 to the fourth grams per minute because ammonia is the limiting reactant. Okay, so I hope you noticed kind of right off there that this was a limiting reactant problem. All right. So molar mass of a gas. We can use the ideal gas equation to figure out molar mass. Now here, you see your equation. The molar mass of your gas is, so again, remember rho, that's Greek letter rho, that's density. So density times R times T divided by pressure. But you need to know where some of this stuff comes from. So I say, well, what is molar mass? It's grams per mole. Or I can rewrite it as mass over number of moles, which means I can rearrange this to be number of moles times the molar mass is going to equal the mass of whatever compound I have. And then number of moles is going to be mass over molar mass. Okay, so then we can go straight into our PV equals nRT. Okay, so then I'm going to replace N with my mass over molar mass. Okay. I probably don't have to scrunch it into the side like that. Okay, then I'm going to multiply through. So bring that, that's going to be mass RT over molar mass. Now I'm going to move, so this is times V. So now I'm going to get pressure by itself. Let's see. Okay, so then pressure divided through by volume. So it's going to be mRT over volume times molar mass, which we can separate out the mass over volume. Mass over volume times RT over molar mass. And what is mass over volume? Do you remember that? Mass over volume is our definition of density. Okay. And so when I multiply the rho back in, it's going to be rho RT over molar mass. Okay, so then I'm going to this. So then remember, I'm trying to get an equation for molar mass. So I'm going to multiply through by molar mass. Okay, so that's going to give me pressure times molar mass. It's going to be density times R times T. Now divide through by P. So then I'm going to get the molar mass of my gas is going to be density RT over P. And that's the formula we had above. But you need to make sure that you're going through these derivations and understand where things come from, because your next assignment, you're going to be asked to do one. Not a difficult one, but you're going to be asked to do one. Okay, so next exercise. A compound has the empirical formula CHCl, a 256 mil flask at 373 Kelvin and 750 torr contains 0.8 grams of the gaseous compound. What is the molecular formula? Okay. What are we being asked for? Okay, well, let's see our volume. We also know that 256 milliliters is 0.256 liters, because remember, liters is the unit that's in the ideal gas constant. Temperature, 373 Kelvin. Pressure, 750 torr. We'll have to change that because we need atmospheres for the ideal gas constant. Our mass that we're going to be working with is 0.800 grams. Carbon grams per mole. Hydrogen chlorine and then of course our gas constant. Okay, so we have our list of things that we know that can help us solve the problem. I know that I'm going to need pressure in atmosphere, so let's go ahead and do that. When we talked about these conversions, so we remember that there's 760 torr per atmosphere. That's going to give 0.987 atmospheres for our pressure. Now, you remember that we need, for the empirical formula, we need a multiplier for our subscripts. And so we need the molar mass of the empirical formula. We also need the molar mass of our actual compound. And remember, we're going to divide those two to get that multiplier. So same idea as last time, we just have to go about getting the molar mass in a different way. Okay, so molar mass is density times R times T over P. We don't have the density of this compound, but what we do have, remember, density is mass over volume, and we have both of those. So our molar mass is going to be mass times R times T over volume times pressure. All right. Now we're ready to plug in numbers. So we have 0.800 grams of our compound, our gas constant, our temperature is 373 Kelvin. Our volume, and then our pressure is 0.987 atmospheres. When we multiply this all up, our molar mass is going to be 96.9 grams per mole for our actual compound. Okay, well, let's look at the empirical formula. CaCO, it's going to be C plus H plus chlorine, or 12.01 plus 1.01 plus 35.45 equals 48.47 grams per mole. Now I have the two numbers that I need to find out my multiplier. Okay, so remember, that's going to be my molar mass of my compound over my molar mass of my empirical formula, or 96.9 over 48.47. That's going to give me 1.999, which of course we know we round to 2. molecular formula. So of course, this 2 is going to multiply all of the subscripts. And if you notice CHCl, all the subscripts are 1. So it's going to be C1 times 2, H1 times 2, Cl1 times 2. That's going to be C2H2Cl2. And that's your molecular formula. Something you don't have to know. This will be more of like when you get to organic chemistry, but this is called dichloroethylene. Now, do it in a different color so you know it's not part of your solution. Now, in organic chemistry, you'll learn that anytime you see an E and E ending, that's going to be a double bond between your carbons. So C2, and then I'm going to do this version of it. There's 3 different versions. This is the trans version, and the trans is we're looking at our exterior ligands, which are our chlorines and hydrogens. And what you notice is that the chlorines are on opposite sides of the molecule, so trans means across or opposite. And so that's why this is the trans dichloroethylene. All right, Dalton's law of partial pressures. So a partial pressure is like, say you have a bunch of gases mixed in a container. The partial pressure of an individual gas is how much pressure that gas would have in that container if none of the other gases were present. And so what Dalton found is that if you just take the partial pressure of each gas and add them all together, that gives you that will give you the total pressure of the system. So here, of course, Greek sigma, or that's our symbol for sum. And so that just means you're going to sum over the index. So your index is I. And so it just depends on how many different gases are in the system. You have partial pressure 1, partial pressure of gas 2, partial pressure of gas 3, so on and so forth. So like the way we represent partial pressures, let's say we have a mixture of helium, nitrogen, and methane. So your P1, P2, P3, those would actually be represented by pressure of helium, pressure of nitrogen, pressure of methane. So when you see pressures like this, these are going to be your partial pressures. Now, another way to write Dalton's law is you could have in total, which is number of moles, times RT over V. And of course, in total, you see your sum here over your various moles. So this would be like N1 plus N2 plus N3, so on and so forth. That's your in total. Now, I did leave space here to do the derivation to get from here to here, but that's actually going to be part of your next homework assignment. You're going to have to go from one expression of Dalton's law to another, where your key is remembering that according to your ideal gas law, nRT over V. So that's, if you want to start working on that now, that will be a problem on your next assignment. So you notice that your RT and V are all constants. These are going to be gases mixed in a single container, so they're all going to experience the same well, R is a constant, but the same temperature and volume. Okay, so let's look at a mixture of 1 gram of H2 and 1 gram of helium in a 1 liter container at 27 Celsius. What is the partial pressure of each gas and the total pressure? Okay, so I'm just going to put P sub I because that indicates it's like, well, what is the partial pressure of hydrogen? What is the partial pressure of helium? And so it's just, we need each partial pressure. And then at the end, we also need the total. Okay, so things we know, the volume of our system, 1 liter, temperature, 27 Celsius. That does not match the gas constant, so we will change that. Hydrogen. Let's see, helium. And our gas constant. Okay. So let's start using the ideal gas law to figure out our partial pressures. Okay, so partial pressure of H2. Okay, so this is how you start to set it up. So again, your V, R, and T are constants. So your pressure is going to be dictated by number of moles. Okay. Well, that means my pressure Q is going to be N of H2 RT over V. Okay, well, how many moles of H2 do I have? Well, I have 1 gram of H2. H2 has a molar mass of 2.02. This is going to give me 0.495 moles of H2. Okay, so I can plug that in now. And so my pressure of H2, or my partial pressure of H2, let's also remember rule to follow. Don't set alarms when you're doing a class. At least I was able to get that email out to the vice president, but you know. Okay, so let's see, our temperature is 27 Celsius. That is going to give us 300 Kelvin. All right, now we can finish this problem. So our number of moles is 0.495 moles of H2. Our gas constant, 0.8206 liters, atmospheres, moles times Kelvin, 300 Kelvin. And then our volume, liters. 1 liter again seems redundant. Like you're like, oh, what divided by 1? I don't even need that in there. Just go ahead and continue to put it in. We're just making sure we're doing every step until we're comfortable with how these problems work. So our pressure of H2 is going to equal 12.2 atmospheres. And that is that first partial pressure we're looking for. And again, I can set it up using the ideal gas law because remember, this would be the pressure of H2 in that container if the helium wasn't present. So I can just use the number of moles of H2, plug everything into the gas law, and get that pressure, which means that for helium, I can do the same thing. Okay, so just use the same equation, pressure of helium. This time it's moles of helium, RT, over the volume of our system. Okay, well, let's see. What are our moles of helium? Well, remember it's 1.0 grams of helium. And then helium is 4.003 grams per mole. So that is going to be 0.250 moles of helium in the system. So then my pressure of helium, okay, so that's going to be 0.250 moles. All the other numbers are the same. Okay, and then we multiply this all up. Our partial pressure of helium is going to be 6.15 atmospheres. Did I write down the units? Yeah, I did. So there is our second partial pressure. Now the only thing we need left is total pressure. So remember Dalton's law. In this case, we just have our two gases. So it's going to be the pressure of hydrogen plus the pressure of helium. It's going to be 12.2 atmospheres plus 6.15 atmospheres. Total pressure is going to be 18.4 atmospheres for our total system. So Dalton's law is pretty straightforward. You're really just finding your partial pressures and adding them all together. All right, let's finish up with our last topic of this. Which one was I going to have you derive? Is it this one or the last one? You can do the Dalton's law on this. Same idea. Okay, so mole fraction. Mole fraction of a system is going to be, so it's like here, so this is your Greek letter chi. Well, I won't see you in the classroom, but every year I have students who go, oh, it's chi. And I want to slam my head in the door. No, these are Greek letters. These are Greek letters. They're not talking about a person's internal energy from an Eastern mindset. Um, so it's the Greek letter chi. But so you see here, we have chi, our mole fraction of whatever compound one is. And so that's going to be your moles of that compound divided by your total moles in your system. Okay. So another way that mole fraction can be written is in terms of pressure, where it's going to be the partial pressure of the compound you're looking at over the total pressure of the system. How do I get from one to the other? First off, I'm going to say PV equals nRT. So N, number of moles, which is the primary number in our first representation of mole fraction, is PV over RT. Now, you remember when we're working with, so here we have the moles of just one of our compounds over the moles, total moles, so it's the moles of each individual compound. And when we're working with partial pressures, we know that your pressure will change along with number of moles, and V, R, and T are constant. So we can separate these out. So the number of moles would be P times V over RT. Okay, so that means that for N1, so for compound one, it's going to be P1 V over RT. N2, it's P2 V over RT. N3, it's the partial pressure of compound 3 V over RT, and so on and so forth, however many compounds we have. So if I say that the mole fraction of compound 1 is the moles of compound 1 over total moles, I can then say that N1 is partial pressure 1 V over RT over okay. I can expand this into, now if you know your summations, you can cancel out now, but I don't know how many of you have worked with those. So we're going to go ahead and expand things. All right, so on the bottom, we're going to have P1 V over RT plus P2 V over RT plus P3 V over RT. And then, of course, you could continue this on to however many you have. I see then on the top, you're going to have partial pressure 1 V over RT. Okay, I'm going to, I see that every pressure is multiplied by the same constant in the denominator. So that's going to be P1 plus P2 plus P3 plus so on and so forth out to however many gases are in this system. So I'm factoring out the V over RT. And now I see V over RT is a constant. So that's going to divide out. And I end up with, let's see, our denominator is P1 plus P2 plus P3 P1. And so you see that, again, our mole fraction can be represented. You need to know how to get from one expression to another. Like, where did this stuff come from? You need to start developing an understanding for that. So you'll work on that on your next assignment. It's very close to, it's the same kind of process we did here. Like, where am I at? Where am I going? What do I have that I can plug in that can start to get me there? Okay, exercise. So 50-liter rigid container holds certain mass of H2 and the same mass of helium. That's great. We don't know what those masses are. The total pressure in the container is 3 atmospheres at 25 Celsius. What is the partial pressure of H2 in this container? So I only need one of the partial pressures. This is kind of a fun problem. Okay, so partial pressure of H2. My container, 50 liters. The total pressure is 3 atmospheres. temperature is 25 Celsius. Let's see, helium is 4.003 grams per mole. Hydrogen is 1.01 grams per mole. R okay, so I have that. And then I don't know how much I have of each. I'm just going to say I have X. Well, I'm going to make that look less like a chi, but X grams of H2 and helium, because the problem said I had the same mass of each, so it's just X grams of that. Okay, well, I wrote R down. I mean, this is a good lesson. I wrote R down, but I end up not needing it, so that's fine. Again, you want to make lists of things you might need to solve this problem. Okay, so our molar mass, not molar mass, our mole fraction, we're solving for the partial pressure of hydrogen. So we want the mole fraction of hydrogen. Moles of H2 over total moles. Okay. So how do we do that? Well, let's get an expression for moles of hydrogen. Or H2 is 2.02 grams per mole. So I have X grams of hydrogen. And that's going to be 2.02 grams per mole of hydrogen. That is going to be X over 2.02 moles. Let's separate this out to 1 over 2.02 times X moles. And 1 divided by 2.02 is going to be 0.495 X moles of hydrogen. We'll do the same thing for helium. Oh, wow. I think I need more room. Oops. X grams of helium. Go ahead and put that in now. Dun, 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 dun. Okay, so helium is 4.003 grams per mole. And when I do my 1 over 4.003 X moles, that's going to come out to be 0.250 moles of helium. Okay, now my mole fraction. Moles of H2 over total moles. So 0.495 X plus 0.250 X. And then we have 0.495 X. This is going to be 0.495 X over 0.745 X. You'll notice that the X conveniently cancels out. 4.95 divided by 0.495 divided by 0.745 is 0.664. That is the mole fraction. And mole fraction, keep in mind, has no units. So the mole fraction of hydrogen in this system of mixed gases is 0.664. So that means the system is about 66.4% hydrogen. Okay, well, I also know, I hate shoving things together like this, but I didn't have enough room. So we also know it's the partial pressure of hydrogen over total pressure. And what I want is partial pressure of hydrogen. That's going to be mole fraction of hydrogen times total pressure, or 0.664 times our total pressure is 3 atmospheres. So the partial pressure of hydrogen comes out to be 2 atmospheres. And when you're doing assignments, make sure to leave yourself plenty of room. Don't squish things together like this. I hate this. I've already added another slide to make sure I account for that. But this is how you use mole fraction. All right, so we're going to finish this chapter up tomorrow, maybe start chapter 6. Let's see. Talk about the exam tomorrow because it'll be posted on Friday, but it'll be due on Monday. So, yeah, what we're going to end up doing is whatever we get through by the end of Friday is all fair game for the exam. So, because it'll post it on Friday, you'll have Saturday and Sunday to get it done, which will give you time to look through the videos, but it'll all be fair game. All right, talk to you tomorrow.